So last time we talked about direct forecasting method. We are trying to predict the entire forecast horizon at once. And also this autoregressive forecasting method, which we predict one time step at a time. And the benefits of doing this autoregressive forecasting method is that if we during training, maybe we train the model to predict 24 steps ahead. But at test time, we can predict different number of steps. So if we at test time, maybe we can predict 30 steps or even 40 steps. So this kind of flexibility is what makes this autoregressive model stood out compared to just a direct forecasting method. So today we'll dive more deeply into this autoregressive method, and we'll also talk about one very famous method called DeepAR. So I'll start with some refresh from last week. So this is the iterative method, and this is a simplified version of an iterative method. So some examples of an iterative method will be RNNs or LSTMs. So what you do is that you will have a memory vector, and this memory vector is thought of to summarize all the information from the past. And you will concatenate it or do some other kind of operations with your feature vector from the current time step. And you feed into a neural network and you expect two outputs. One is the updated memory vector for the current time step. And second one is the prediction for your target variable or whichever other variables are also missing from the next time step. Yeah, so this memory vector is something that you pass along throughout the time steps. Yeah, so last time, so this is the same picture from the last slide, with the exception that I want to highlight here is that if you directly predict the target variable based on this memory vector, in that sense, you're kind of only having one layer of the current neural network. So if we want to stack multiple layers, which we know that's where the expressiveness of deep learning is coming from. So if we want to do that, you'll make some changes for the first layer as well as for the subsequent layers. So for first layer, what you care about is just to update this memory vector. So if you start out with a memory vector from time step t-1, and you combine it with a feature vector from time step t, you feed into a linear layer followed by a tanh for activation function. You'll be able to update your memory vector for the current time step t. And then if you have, so this is what happens with the first layer, and you have all the layers that follows it. What you will do is to take the updated memory vector from layer n-1 for a current time step. And then you'll combine it with the memory vector for the current layer n from last time step. So combine those two memory vectors together. So note here that in the first layer, we have this feature vector. And the vector at the bottom on the right half, so this layer n-1 is kind of like there to replace this feature vector. So you take those two memory vectors and you do a linear layer to get the updated memory vector for layer n at the current time step. And if that's the last layer, that's when you do the additional linear layer based on this memory vector to get your final feature vector. So you don't really care about all the memory vectors from the previous layers. You only use the memory vector from your last layer to compute this target variable. And this is another picture if you have 3 layers. So you see that the target variables at the very top are only computed from the memory vector of the last layer. And if you want to write all the math behind both of those 2 layers, 2 types of layers, then you have the one linear layer from this memory vector. So this is actually the second half. So you have the HT-1 WHH transpose plus BHH. So this is a linear layer based on this memory vector. And you also have the linear layer based on this feature vector. And you add them together. So they will be equivalent to just concatenating and do a linear layer altogether. And the same thing for the right-hand side. So you have the memory vector from the current layer and also the memory vector from the last layer, but for the current time step, then combine those together and feed into a linear layer. And one issue that you might have heard of is that if we have a simple RNN, a very common issue is a vanishing or exploding gradient problem. So where that's coming from is that if we have a very long window, so if we have to go through many time steps, we're kind of recycling this wave vector W for each of the time step. So it appears at the first time step, appears again at the second time step, and it appears many times. And if you want to draw the computation graph, you will see that the W is actually involved many times. And then if you then take the derivative, you'll find that if you go back long enough, because you're recycling the same W, this part in the middle here is either gonna explode or it will go somewhere near zero. So you want to avoid that to get some stable gradient. So this is the issue with recurrent neural networks. And actually, if you talk about in a more general setting, you just talk about neural networks with many layers, you often also have this problem of exploding or vanishing gradient. So this is a kind of like a detour from the RNNs. So if you have a network with many layers, there are some solutions that you can kind of mitigate this issue. So one thing you can do is to use the ReLU activation function. So ReLU is where we take out all the negative parts and cut it to 0. And for all the positive parts, we use the identity function. So compared to sigmoid, which everything gets in between 0 and 1, which if you have many layers or you stack many of them together, you'll like multiply all those numbers between 0 and 1 together. So get a number very close to 0, which you can kind of solve this issue with ReLU. And the other thing that's very famous is this residual connections. So in addition to have the X going through the stack layers, you can also have a shortcut that directly adds this X to the output layer. So if you calculate the derivative, maybe the part in the middle might somehow vanish, but you'll always get some gradient that's going back to X from this identity function. So from this shortcut here. Yeah, and for residual connections, a very famous example is ResNet. And last thing you can do is to do this batch-wise batch-wise normalization or layer-wise normalization. So for here, we need to look at the vectors as kind of vertically. So there will be 3 vectors in this batch. And how batch normalization works is that you compute the mean for each of the elements across a batch. So for the first element, you compute its mean, and it's actually not 3. But I think it's close enough to 3. But you basically just compute the mean and compute the standard deviation for each element, and you normalize based on every element. And for layer normalization is when you have this, for each vector in the batch, you compute the mean for across all the elements in that sample vector. So here we have 3 vectors, and each vector have 6 elements. So we'll be computing the mean and standard deviation across those 6 elements. And then you do the normalization that way. So this, if you have many layers, that kind of prevents some of the entries from one layer from getting either too small or from getting too big. So for both batch normalization and layer normalization, you can put it anywhere in the model. It's not just in the input layer. You can put in some, where you can put it, apply it to some layers that are more of the intermediate layers. So this will kind of help with the exploding or vanishing gradient problem. So back to the RNNs. So if we have this exploding or vanishing gradient problem, one solution is to add this long-term memory into the RNN. So this will be called a long short-term memory network, or LSTM. So in addition to the vector H, which we had before, which is intended more for the short-term memory, we'll also want to introduce another vector C that's intended more for the long-term memory. And the basic idea is, so we always have this C that's going from the previous time step to the next time step. But not like H, which we completely discard all of its components. For C, we can kind of compute a portion, like a ratio of how much we want to forget and how much we want to update at each step. So there are actually a lot of formulas on this slide, but it's not important to memorize those formulas. It's more important to just get a overall picture of how those C get updated, so you can have an idea of how this will help with exploding or vanishing gradient problem. And actually, a few years back, this is actually a very popular question that people ask during interviews. So the first number that you will compute is based on this H and X. So X is the input vector from this time step, and you have the H from as the same as the short-term memory or the memory vector from previous time step. And you take those two, do a concatenation, and pass it through a linear layer to compute how much you want to forget for each of the elements in your long-term memory vector C. And based on this, you'll compute another number for how much you want to update and what you want to update with. So all of those are entirely just based on the concatenation of the memory vector H and your feature vector X, and you pass them through a linear layer, but of course with different linear layers. And based on this, how much to forget, you'll multiply this C from last time step with this F, and then you add the components that you want to update, which is this C tilde here. And this will be your updated long-term memory vector C. And finally, you process it with an additional linear layer to get your the output short-term memory vector H. So it's this part is same as before. So whether it's RNNs or LSTMs, every time steps that you want to compute output, you'll always use this short-term memory vector H. Yeah. And again, don't worry too much about all the math here. You don't need to memorize all the formulas, but the main picture here is to understand where this C is coming from and how it helps with this memory or exploding and vanishing gradient problem. And one thing that's very important to keep in mind here is that when you compute this, how much to forget or how much to update, you don't apply the same number across the entire memory vector. So for your memory vector, because it's a vector, it will have many entries. So don't apply the same number to all the entries. What you do instead is to compute one number for each of the entries. And for each entry, you can compute how much you want to forget or how much you want to update. Okay, and after we covered LSTMs, I think it's good time that we give a more concrete example of an autoregressive network. So here, a very famous paper is called DeepAR. So this is the same picture that we have from before. We will have this recurrent neural network, whether it's RNN or LSTM. And at every time step, we have this short-term memory vector H. And based on this memory vector, we can apply a linear layer to directly get a prediction for that time step. And for DeepAR, what it does differently is that instead of directly predicting that number, so you directly predict the target variables, you'll predict probability distribution. So first compute a probability distribution for that time step, and then based on this distribution, you can draw a number, or you can take the mean, or do other things based on your distribution. So one example is for every time step, maybe we can choose to predict a Gaussian distribution. So to predict a Gaussian distribution, what we want to do is that at every time step, you'll be predicting a mean, which is this mu here, and also the standard deviation, which is a sigma. So based on those two numbers, you'll be able to get the Gaussian distribution. So how you get those numbers? First, you can apply a linear layer based on this short-term memory vector H to get a mu. And for a sigma, we need to apply an additional activation function called salt plus because we want to make sure that the sigma is always positive. And the other parts are still the same with linear for the still the same as for the mean, which you just apply a simple linear layer. So when you're training this network, you'll be computing this likelihood for every time step. So this is the same as if you think about the PDF or the probability density function for the Gaussian distribution. So if we predict the mean and sigma, we'll be able to get this blue curve here. And based on the ground truth that we actually observe, we'll be able to see what's the likelihood, given this Gaussian distribution that we computed, what's the likelihood of observing this ground truth that we actually observe. Yeah. And this is where this likelihood function is coming from. So it's same as the simple Gaussian distribution here. So when we do the training, we actually want to not only to optimize for every step, we want to have a forecast horizon that we try to optimize. So this is a second line here, which we have z, which is our target variable, and you want to optimize it for your entire forecast horizon that goes from t naught to big T. But if you directly optimize this products of the likelihood across the entire forecast horizon, it's kind of similar to the gradient vanishing or exploding problem that we have had on the previous slides. So if you have many of those numbers between 0 and 1, and you take the product, it will get very close to 0. So that will cause the gradient to be very unstable. So what you can do instead is to apply this log transformation. So after you do this log transformation, instead of having this product, you're having a summation across all the local likelihoods that I want to maximize. Okay, let's continue. So for DeepAR, so I talked about that we have two baselines I want to implement. So the first baseline that I want you guys to implement is this DeepAR model. So what we cover here is actually the most important part from the DeepAR. And there are still some of the other stuff that we can talk about. But the most important parts are at each step, instead of predicting the numbers directly, you want to first parameterize the distribution and then draw a number from this distribution. Okay. Then let's take a closer look at the DeepAR paper. So this is the abstract from the DeepAR paper. Maybe I will give you guys a minute to skim through this paragraph. Okay, so personally, I think the DeepAR paper has two parts that are very important. So the first part is so instead of predicting this numbers directly, we try to predict probability distribution. And by doing this probabilistic forecasting instead of point forecasting, we'll be able to, if we care about the confidence interval, there will be ways that we can extract the confidence interval from this probabilistic distribution or probabilistic forecasting that we do. And the other thing is that if we have, so traditionally, if we have ARIMA models, for every variable, you'll try to fit the ARIMA model independently. And here, if we have many related time series, so if we think about a grocery store, there might be many products in the grocery store. So instead of training a separate model for each of the products, we can actually train one model that's shared across all the products. So if there's some information that we can leverage from one product and apply it to a different product, DeepAR will allow us to do that by training one LSTM model that uses the same set of weights, which you can apply to other products. Okay, sorry, the text here are a little bit long for those two slides, but maybe I'll also give you a minute to read through those bullet points. Okay. So this is actually the same contributions. So I just took the text from the original paper and pasted it here. So if you go to the original papers, it will have the same items as they listed as their contributions. So I guess when you're reading a paper, maybe one very important part is to being able to understand what their contributions are. And this itemized list will help you to better understand their contributions. So the first item that they mentioned is having this deep learning method, you'll no longer need to do manual feature engineering. So this can be kind of thought of to be applicable to a lot of the deep learning methods. And second item here, which we'll cover during our next meeting, is that having this probabilistic forecasting will allow you to draw a sample for a forecast horizon in a way that you can generate a confidence interval for your forecast horizon. And third item is that going back to our grocery store example, so if we share the same set of weights across all the products, and maybe in the future, if our store decides to add a new product, and this product is called a co-star product because it's an item with very little history. So if we can leverage the weights from the other products and apply it to this product, we'll definitely get a much better performance compared to training a new model from scratch based on this very limited history for this product. And last contribution that they mentioned is that instead of just using a Gaussian distribution, you can actually generalize it to different distributions. So maybe if you have some kind of a skew distribution, you can also choose to parameterize the skew distribution instead of just assuming Gaussian noise in your model. Okay, and this is the last part I want to cover today. So this is a picture that we have from before for DeepAR. So this part is a context window, and remember that for one given window, you can cut it into two parts. So the first half is called the context window, which will have the ground truth for a target variable. And what we want to predict is this right half. So it's our forecast horizon. So if we think about the DeepAR model in terms of a seek-to-seek model, then the first half can be thought of as an encoder, and the second half can be thought of as a decoder. So it's the same seek-to-seek idea as in NLP, which kind of for an encoder, you are trying to summarize all the information that's given. And then for a decoder, you're trying to do the predictions, maybe autoregressively here. So there are different ways that you can learn those encoder weights and decoder weights. Maybe you can share the same set of weights for the encoder as well as for a decoder. So you can maybe have the same LSTM for the encoder and decoder. Or you can choose to have the encoder to learn their own separate weights and the decoder to learn its own separate set of weights. So those choices are completely up to you. And when we calculate the loss function, when we calculate the loss, you can calculate the loss based on both the context window and also maybe for your forecast horizon. Actually, you probably always want to calculate the loss based on your forecast horizon, but optionally, maybe you can also have the loss in your context window as well. So this is also another choice that you can try out once we implement DeepAR. So whether we want to incorporate just the loss from decoder or you want to incorporate the loss from both the encoder and decoder. And there's another thing called teacher forcing here for those autoregressive models. So recall that for autoregressive models, at inference time, because we don't have the ground truth for this, if we look at second time step, we will not have the ground truth for this T naught plus one. So at that time, we need to get our prediction from previous time step and then fill in that missing target variable. And then for each step in your forecast horizon, you always need to do this. So what teacher forcing is doing here is that during training, if we use our own predictions to make more predictions, it will maybe lead to very slow convergence because by the time that we get to step T naught plus two, maybe we already have a very big error for T naught plus one. And based on this number with very large error, we probably not be able to get a very good prediction for T naught plus two. So what you can do instead during training is that we always use the ground truth for a target horizon. So instead of using our prediction, we always use the ground truth. So this can be think of as a kind of a curriculum learning to make the task easier to start with. Okay, and this is all I have for today. And next class, we will talk a little bit more about how to extract the confidence interval from this probabilistic forecasting, as well as I'll show you some code to set up the server and GitHub.